So for the past 30 years, the GPU has been the engine of digital innovation, accelerating science, rendering world, rendering video games, and pretty much redefining what we can do in computing. But what does it mean to create a new GPU from scratch, chip by chip, architecture by architecture? And most importantly, why would we do that, right? What does it mean for you, for you, for you? What does it mean for you as a community of supporters of open source or whatever you do? And the question is legitimate. GPU market right now is a billionaire market in the hands of a handful of companies. So it's a big challenge, right? But I'll talk about this in a moment, how do we approach this kind of challenge and why it's not really a challenge. But let me talk a little bit about who we are. So we promote lowering the barrier to entering a new generation of computing through GPU, especially accessing unprecedented quality in computer graphics and in scientific simulation. As you know, if you want the top in this area, you need to pay big dollars, and that's a very old, it's a very old type of problem, right? And we are member of several open source initiatives, as you can see here, and proudly we are corporate sponsors of the Blender Foundation because we believe in giving back after using so much of the open source. So this is the spirit of open source, right? When you don't have much, you can get, and it helps you grow. It helps you put you where you want to be, put you on the road. But then, after a while, if you can, it's good to give. It's just normal to give back, just moral. So, what is this? We talked about challenges, and I decided to start with talk with a fun story. So. Some of you, or probably all of you, will be familiar with the story of Columbus' egg. And so as to recap, so when Columbus came back from crossing the ocean, he faced his detractors once again. Those who told him, it's impossible, you cannot do that, right? You're going to die, the earth finishes, whatever the reason was. And they probably weren't happy that he actually came back with something. And they said, well, anybody could have done that. You just went straight and back, right? Anybody could have done that. So he challenged them. He said, picking up chicken egg and said, make it stand on the table. And they tried to balance, and they couldn't, and they failed. And then they said again, it's impossible. You can't do it. You can't make an egg stand on the table, right? So Columbus, according to legend, takes the egg, gives the little tap. The egg, slightly crushed, stands on the table. And what do they say? They say, you cheated. Anybody could have done that. So he said, well, yes, anybody could have done that after you see how it's done. So it's obvious what the story wants to tell, but for me it has a deeper meaning. And the takeaway from the story can actually be broken down more significantly. What does make a person say something is impossible? Because I think many of you are probably were in that situation sooner or later. I've been in that situation several times. Someone tells you, your colleague, your boss, an expert, it tells you can't do this, and then you do it. So why did they do that? Because there is a difference in approaching challenges in general. The pragmatic person is not unintelligent. Your boss is not unintelligent. Your colleague is not. They're just trapped. They're trapped because they are focusing on the how do I do that, right? Right now, with the tools I have, with the status quo, with what I believe, how do I do that? So they start from there, trying to figure out how to get to the goal, right? So as you run a mental catalog of the things you know, the things you believe, the things that you can see, you can't find a way, and then you will say, it's impossible, or at least it's really hard, we missed something important, right? But the innovator thinks differently. He reverses the process. He focuses on the, what is that we're trying to do here? Right? What is it really that we're trying to do? Break it down. The egg is supposed to stand on the table. Did we ever say the shell of the egg should stay intact? So once you drop that, assume constraint, the space of solutions explodes, right? And of course, the solution is most likely to be unorthodox. It's something that wasn't expected, that people weren't thinking about, because they are trapped in that thinking of, how do I do, the normal way. But it doesn't matter, because once you solve your customer needs and wants, they're not going to judge the way you did it. They're just going to give you the money and say, give it to me. That's great, right? So how does this apply to us? So this is the Zur GPU, our baby. This is the entry level, one chiplet. How do we approach the challenge, and what was the Columbus egg for us? It's very, very simple. Once again, we started from the what is needed, right? And to understand what is needed, we spoke to many, many people. We spoke to people from all walks of life. Gamers, game producers, scientists, institutions, even governments, all sizes. And we asked them, are you happy with the current GPUs? What do you think is missing in current GPUs? If you had the ability, what would you change? What would you want to have? What do you need? Okay, and we saw patterns, because despite being people coming from everywhere doing different things, science or games or whatever, the answers had patterns. So we took those patterns and we understood, okay, let's package this thing, these needs and wants, let's package them into product. And this is what we're looking at today. At the core of the GPU is a RISC-V RVA23 processor, which is going to run Ubuntu out of the box. I mean, 2510, 2604 LTS run out of the box on RISC-V. With RVV vector extensions, this is our answer to the closed architectures, the closed systems, the closed ecosystem of software and compilers. This is completely open, because that means you can run your open source software in there, as long as tool chains allow for that, which they do for most things. You can take OpenCV and compile it right there, running on the GPU directly. The second thing is this. This is the one I love the most. This entry-level board, which is actually quite cheap, comes with 32 gigabytes of LPDDR5 memory, but it has those sodium slots. Because the other thing that everyone said was why, we need more memory on our GPUs. And right now, the pricing model of GPU is kind of like the cloud pricing model. If you can't buy more memory unless you buy also more capability. And then the price scales very quickly, $6,000, $8,000, $10,000, $20,000. But it doesn't have to be that way. So on this board, you can expand your memory up to 160 gigabytes. That's the entry level. We have a dual slot version with 2 chiplets, where you get either 64 or 128 gigabytes base, and you can expand it to 320 or 384 maximum. And then we have the data center version for chiplets, which expands up to 2.3 terabytes of memory. And we'll see in a moment what that means. This is not just answering to what users want. This is also innovating, because we are taking GPU to the next level. When you have this kind of characteristics, the question is not just what can you do the way you do it much better, but also what new things we can unlock. So this is pretty much part of this talk today. But let's continue a little bit. 400 gigabit Ethernet on board on every model. Our founder, Darwesh Singh, his background is hyperscaling. So you can imagine what you can do with that, especially in data center nodes. But there also are users who specifically, yes, especially in the scientific community, they wanted something like this for tackling latency in processing large amounts of jobs. And I think we can just mention the power consumption of this board is 120 watts. And the power consumption of the dual slot is slightly below 250 watts. So that's the other thing that we really wanted to achieve. We're very happy with that. So let me talk you through a cross-section of things that we do, because obviously you can imagine creating a GPU from scratch is a huge undertaking, and it taps into pretty much anywhere, anything that you can consider computing. So I just took a selection, and I created a bit of a story for you to share with you. Let's start with hardware development, because this was the interesting one for me as well, because I'm coming from software, and I didn't know much about hardware before getting into these kind of things. So the interesting part with hardware development is that I wish I could tell you that there was a little army of small monkeys doing prototyping or people drawing on glasses like in movies, but it doesn't happen that way. Creating hardware is actually programming. You program hardware, right? You program hardware through hardware description language, usually either VHDL or Verilog. We use Verilog. And you literally describe the architecture. You literally describe the functionalities. And it's a little bit different from how you will say, I program C++, I program C, but it's still programming. And that means two important things, two important consequences. The first consequence is that the methodology in developing hardware, it becomes pretty much very similar to software methodology. You have repositories, you have peer reviews, okay? You have reusable modules, and that is a great help. It's a great optimization from management point of view, okay? Because it's not something, it's not like a different department, people doing completely different things. It's very similar. And in this example here, for example, this is an architecture. We dive into the architecture. We see individual component. All of this is described through software. And then the software goes down the road, and we'll see a little bit more details soon. It becomes a layout, and then it becomes a wafer. That becomes the actual chip. Okay? So this is an important thing I wanted to stress on. How do we test it, though? Because if you write C++, you compile it, and then you compile it targeting a specific fixed architecture, like x86, and then you can run it, instructions by instructions. But how do you run a software that describes hardware architecture and functionality? So for that, we use FPGAs, field programmable gate array. These are special boards. Some of you probably know what I'm talking about. These boards reconfigure themselves. Once you flash them with the software, they reconfigure themselves, and they become the hardware that you're trying to simulate. They literally become the hardware. The limitation is there, of course. The scale is different. They are much, much slower. But nonetheless, they are the hardware. So you can write the register into the registers. You can write into the memory, map the memory, and they behave exactly like the final hardware. And you can test. You can see what's happening. Do they work as expected or not? You can fix bugs, go back to the software, flash it again, and it's a process. So again, very important to understand, once you write this type of software, you don't have to do anything else to create the actual chip, okay? The software is flashed into the FPGAs, so you can test it, you can do your development cycles, but the same software goes straight to the factory and becomes the chip. The problem is that this part here costs millions of dollars. So you cannot do it, like every 5 minutes or every week. You can't say, hey, we're ready for a new, we want to try this one you want. So you really have to get it right. And that's quite important for this talk. You need to get to this point and be really confident you got it, okay? Of course, contracts with factories include pre-tape outs, so you can do small iterative tests before getting to the big one. But once you do it, that's it, you lock it in. There is no click here to download a new upgrade like we do in software. That doesn't happen, so you need to get it right. So let's now talk about software development, because it was the core of this talk. We saw the hardware part. That was I thought it was necessary to understand what we're building on and to explain what we're going to talk next. So when we talk about software, the very first layer is obviously the driver software, okay? Because once you have the hardware is mute. It doesn't do anything for you. It's just sitting there, right? So and how do you control it from high-level software if you want the hardware to do something like specific? You need a driver that takes a high-level instruction and then converts it into writing into registers, mapping memory, and fetching results and coordinating this. On the kernel side of things, we can have multiple softwares on the process space doing this at the same time. So driver development is one of the things we do. At the moment, of course, the driver sits on top of the FPGA, okay? And there's one important thing to say about the driver. I think I'll say that in a moment. And then we have end-user software. Now, this is really the most important part. Because why do we do this? You could say, OK, you guys are creating a new GPU. So once everything is working, once you have unit tests, everything is done, why don't you just give it to someone else that will write the software like everybody does? Well, if you look at other companies such as NVIDIA, AMD, Intel, they also are very much involved in software. There's a reason for that, especially for us, because we are creating something completely new that can potentially change the way we use GPUs. And to be fair, term GPU is a bit restrictive. I know in broader terms, people talk about GPUs, but this one here is essentially like a supercomputer in your computer. So, but we call it GPU because it has ROP, TMUs, it can run your desktop. So we still call it GPU. But so because of all this, we really want to test every edge of what we're doing. And we cannot do that by using just simple unit tests, because once you have high-level software, you have real users trying all kinds of things, right? Combinations of things. And unit tests don't do that. You really want to see how much you can push it. But most importantly as well, the people who are writing this software, which are really clever people, thank God, much more clever than I am, they can actually see through certain synergies of the hardware that we prototyped so far, and they can come up and say things like, hey, there's a situation here where if we do this with the current hardware, you're going to trash the cache all the time. So we really should add this little thing to the hardware if possible, and we can avoid that. We can make it actually faster. And then this information is, of course, is defined into tickets, given to the hardware team thinks about it, and then comes back with the solution, explain, and there's a little bit of loop. So this is the R&D loop, right? And the R&D loop happens because we have this software, which is like our gym, our sandbox, the common place where we discuss improvements on both sides of the coin. So in talking about this, let me introduce the part I specifically follow myself, and it's the Lightning ASIC. So this GPU comes with at the moment, comes with two ASICs, which are domain-specific accelerators, okay? One of them is for ray tracing, and the other one is for advanced scientific applications, floating point 64 bits, i.e. triple standard. The way we accelerate ray tracing is quite different from the way RT cores do at the moment. Not too different, of course, at least in the intent, but it does come as a complete package capable of receiving an arbitrary 3D geometry, and it will automatically compute all the acceleration structures and will be ready for firing queries or arrays. So for those who are not familiar with ray tracing is a technique for rendering, very different from raster. It's the next level of raster, where you can shoot a bunch of arrays into the scene, one per pixel, or multiple per pixels, and then you can understand. So what Lightning does for you, it will tell you, hey, you hit a geometry here. Your array has hit something. So you can decide to simulate a certain material and say the array is supposed to bounce somewhere else and feed it back into the system. So what this allows you to do is to carry information about the light, which initially covers the entire visible spectrum, like white light. And as it hits materials, it can ask the material, hey, what kind of frequency are you absorbing? And the material will say, yeah, I'm absorbing blues and greens, and so you're left with the red one. This is why the cube looks red, right? And then it continues its journey. So if it hits something else, the process repeats. And then if it hits a source of light, it will transfer all the energy back into the light path, and it will contribute to your pixel. That's the basic functionality of a naive ray tracer. The next level of ray tracing is path tracing. So we are developing a solution called Glowstick. It's an advanced path tracer. I don't know if you can see my shoes, but that's what's there. So path tracing is used for absolute photorealism in many, many fields. In this case, well, product presentation, product marketing. The same 3D assets are used for product design itself. Okay, they go all the way to factories. How is it different for a trace? It's not very much different. The mechanism is the same, but it allows to solve the complete rendering equation, which is a very complicated thing to do. And it's very, very demanding from a computing point of view, because you need to shoot thousands of rays per pixel, actually billions of rays in total, many billions, depending on resolution. And historically, it has been used in VFX and motion pictures, offline only, in huge render farms. And what we're trying to do with this new generation of GPU is to make path tracing available as near real-time or real-time technology, which has implications for video game development and many other things. So the benefits of path tracing, like this one you could argue, you can do this with raster graphics. Yes, you're right, in this particular case. So I actually created a short video, not great, quite exaggerated, but you can see the simulated lens of the camera, so it creates a field of view effect. You can see reflections and refractions at the same time, reflections and field of view, all kind of things together. So when you put it into context, it creates something that looks real. So, but I don't need to tell you that. Like if you watch movies and special effects, you can see the difference where reality blurs into the special effects. That's what path tracing does. But like I said, it's a very expensive technique, and this is what we do with the Lightning chiplet. So, of course, in other areas, uncompromised, unbiased, Monte Carlo-based algorithms contribute to realism in architecture, especially architectural design. And the overall benefit that this GPU is adding is the incredible speed and incredible amount of memory. So we hope that also others who are, they've been working for many years on solutions like this one, the rendering engines, can finally find a way to drop advanced algorithms to load and load, for example, continuously, but they can just use all the memory to have it all there and leverage the speed to do much cooler workflows. So this is the reason why path tracing is very expensive. Like I said, once a light ray hits the geometry, it will bounce somewhere, okay? So if you have a specular reflection, it can only bounce in a specific direction. But if you have a more diffuse reflection, it can bounce in many different directions. And which one do you pick? You pick one at random, theoretically. But you really need to hit the same pixel so many times to explore all possible different combinations. So you're solving the integral as you go. And finally, reach a decent solution that minimize the variance between the pixels next to each other, right? And this is why it's so expensive. This is why it cannot be done in real time. So when you see video games talking about we have added path tracing also with RT cores and everything, it's actually a bag of tricks, and it's kind of like a half path tracing. Unreal Engine has a beautiful implementation of, but you only use half ray per pixel, and everything else is quite clever caching and algorithms that deal with pseudo global illumination, whereas this is actually full global illumination. So here's the open source stack that we currently use in glow stick. Most of it is coming from Academy Software Foundation, which you probably saw last year, presenting on this very stage. We have OpenUSD, which is the standard for transmission of 3D geometries and scenes, and how materials are used by objects. OpenUSD is being developed by Pixar. And then we have Open Shading Language. Open Shading Language from Sony ImageWorks. It's actually a programming language for shaders, so for physical shaders, because these are not shaders as you will have in, I don't know how many you're familiar, but it's not the same type of shader you will have in OpenGL or Vulkan, where you actually, it's like a small program defining the effect, right? These are more, it is closer to the causal part of the story, right? So there's the physical background implemented, which is telling you how the material will react to light under certain conditions. So it's still kind of phenomenological, but it's more oriented toward path tracing and physical simulations. And then we have Material X. Material X stands in the middle. Material X tells you how a physical material should be implemented. So it gives a bunch of hints for something like Open Shading Language to create an implementation. And so the purpose of Material X is to say, OK, here's what the material should behave like. So if you want to compile it down to OpenGL or Vulkan or Open Shading Language or anything else, you should have some kind of degree of consistency. So these are actually, if you read between the lines, the features of all these open source softwares are actually addressing many issues in the VFX and motion picture situation, right? And you will say, well, but some of these companies might actually compete against each other in real life. So how is it possible they work together in these open source projects? Well, most of the answer is in the first, in the first talk, but let's just say that a lot of this technology is pre-competitive. So they're not helping each other to compete against each other by creating a solid foundation of open source stacks. They're actually taking advantage of each other, because the competitions happen afterwards in the quality of the movies they release and the quality of the things they do. And with that, the tools themselves don't really have a direct weight, because most of the importance is in the artist. And finally, one other element used from the open source community is Intel Denoiser. This is interesting. It's we call it open image noise. It is an open technology, but it's not open source. You cannot get the source code, but you can still get it and use it as open, with the same philosophy open source. So open image noise is machine-based learning, and how is it used? It's used once you get to the point where variance is really, really small, but it's not perfect yet. You still have a little bit of noise. I don't know if you can see some of the dots. It will quickly instantly turn it into something beautiful. All the noise, the remaining noise is gone, and the image can be used commercially. So let's talk about the testing methodology a little bit, because as you can imagine, between hardware code that goes into the FPGA and creates an architecture and actual billions of transistors, right? They're not hatched in the wafer yet, but they still are in the FPGA. And then you have the driver on top of it. Okay? And then you have all this software and all this third-party software which we take and we need to compile again. This is quite an immense amount of code to maintain and make sure that it keeps doing what it's supposed to do. And the biggest issue we had, is actually subtool regressions. So regressions in general are the biggest problem, right? It's not making a bug. If you make a bug, you realize immediately you can fix it. But regressions happens because of such interdisciplinary and so big and so vast. So let's start from the hardware prototype. How do we test the hardware of the prototype? That's the easy one, because we are using unit test, and the way we talk to the hardware is via DMA. So this is actually pretty important, because it means that we can actually run the driver and talk into the FPGA from inside a Docker container. And that Docker is unmodified. On Ubuntu, without any modifications whatsoever, you run it out of the box in the container and talk to the hardware. This is quite important for automation purposes, I will say in a moment. Unit tests, clearly, they are small programs targeting specific areas of the hardware. So whether it's like writing to a register and making sure you're getting the correct answer, or mapping the memory, making sure it doesn't get corrupted. And these tests are basically Boolean in nature, they're either successful or not successful. And typically, when you want to run a regression test on the hardware, you need to run them all. And if any of them fails, you have a problem, and you need to go there and fix it, obviously. So that's the easy part. Functional tests is a different story. This is where the fun begins, because, like I said, we use Glowstick, we use the high-end software as our R&D sandbox, right? And also for testing that everything works as expected in the hardware prototype, right? And we're using user workflow, so we allow people to do things that are unthinkable. Like, obviously, you give something to a user and say, do something with it, and the first thing it does is the one thing that you didn't think about, or it wasn't supposed to, of course. So functional tests are meant to capture everything that can possibly go wrong in terms of the visual output doesn't match the expectation, or something goes really wrong, like literally crashes, or perhaps there is a regression in terms of how long time did it take to do something. It was much faster last week, what did we do? Now it's half time slower, or perhaps it's twice as fast, that's good. So how do we do that? We need to capture that using functional tests. Functional tests, as you can imagine, are really humongous in size. We add them all the time as we find edge cases, corner cases, or we add new features. We need to add functional tests as well. They, like unit tests, they also target specific functionalities, but they are more complex than that, because in a unit test, you literally code, right, the interaction with the other side. But in a functional test, in a program like this, you need to create an actual geometry that recreates a situation, right? If it doesn't have any textures, it means you're not probably testing textures, right? So if you want to test textures, you have textures in there. If you test in certain cases, like there's a complexity, like rays bouncing in and out, or whatever, you have to have different geometries accurately modeled one by one. And once you do that, the general idea for us is it would be great to avoid users, developers, to block their machine for like a day and a night or a couple of days in running all these tests, because there are so many and they're so heavy. Every test entails a rendering, right? So it's very complicated. So the ideal situation will be when the developer creates a pull request, GitHub actually builds the branch and then runs the tests, and then we can actually see, does it work, or was there a regression? And if it does work, we want this section here to unlock GitHub automatically, right? So that's a complete automation of the CI/CD pipeline. So before we do that, we need to formalize the test. We need some kind of formalism. So what we do, we use JSON, because JSON is flexible enough. As we add new features, as we add new requirements, maybe perhaps new KPIs, we can just add them to the JSON file. We don't need to recompile anything, right? And most of the scripts to run a test are actually in Python. So it doesn't require much energy from our point of view. And some of the information we write in the test, for example, like a truth situation, it tells you, okay, if you run this test, this is what you're supposed to say. So if you get like a rainbow-looking age of statute, you're probably doing something wrong. And the other situation of the truth is KPIs, for example. If you run something like this in those conditions, you're supposed to get at least this amount of rays per second being processed. So if that doesn't match, or something is regressed, or perhaps got worse. And Tests can be also grouped into test sets. So we can actually have different type of tests agglomerated together to test specific areas, like macro areas, like, for example, textures in general, lights in general, or geometries in general. And we can run them individually in case we need. And the tests are actually living in a database. The database becomes like the central, of course, it's the central place where all the tests are living. So that it's one place where we can query, we can maintain, and we don't have an issue in things diverging and having different things on different machines. It's just one place. Where does the database live? It lives in the cloud, of course. So the database itself can grow gracefully accordingly to the process itself, the program itself and the features growing, whether it's in the hardware, new hardware features, or software features. So, as I mentioned before, we want to pull all this together and create a large-scale testing automation because we have multiple engineers working on multiple features. So we have a certain amount of developer branches going on at all given time. And each one of these developer branches carries a high risk of regression every time it gets merged back into the stable branch. So how do we make sure that this never happens in an automated manner? So in other words, the second part of the answer is how do we produce a large amount of renderings? How do we produce the renderings and the KPIs in really large scale? So for that, we create a render farm. A render farm, just like the ones used for making movies by rendering many, many frames, we use it, instead of rendering many, many consecutive frames of a movie, we use it to render all the different tests at the same time. Render farm is pretty simple, logically speaking. We have a client request. In this case, it will be coming from GitHub, or rather our pipeline. We have a submission, so it receives a job request, and the job request carries the information of what kind of test do we need to run, so it can go into the database and fetch it. And then the job is sent to an object called a deadline. Deadline, some of you might have heard something like this last year. It's actually a queue manager and resource manager, which decides where to send jobs in available computing resources in a large network. And then data can be coming from EFS or S3 on AWS. And then we have a results lambda, which is processing the results of the test and packages for the use down the road. So the central element that you saw in the middle, deadline, is like a command control center on the client side. But it really is a queue manager. And the way it works in AWS is we can use it to create resources that we need them, because that's an important thing. At this point in time, we cannot have hundreds or thousands of computers in the house on-prem just to run tests. That would be ridiculous. But when we need to run a large amount of tests, we can have a cloud solution that scales automatically, just spikes in that moment. And then you have dozens or hundreds of computers working together, producing all the reporting for our developers. And that is more financially feasible because the workers are actually spot instances. And the way spot instances work in AWS is like a secondary market where an instance on demand costs, like, for example, $2, $3, but the spot instance is basically unused computing power sitting there idle. And the calculus AWS does is, hey, instead of sitting there idle, I'm going to give it to you for 3 cents an hour, but better than nothing, which is actually quite good because we actually do pay this amount of money because we use many of them. The only snag is if the resource is reclaimed because someone else is ready to pay those $3, we need to let it go. But that's fine because we can be resilient enough to just jump on the next one. So this can never fail. Deadline is quite good because it allows full customization. So we use Python. We don't have to, it's completely software agnostic, right? It doesn't care what you use for rendering and what you use for whatever happens after the rendering. So we do customize it ourselves. And here's the bigger picture, like the complete, like pulling everything together. So we start from GitHub. A developer creates a pull request. The pull request triggers a pipeline. What the pipeline does, it takes the branch. So the branch says, hey, I want to be merged into the stable branch. So this branch is taken by the pipeline. The pipeline compiles it. And then it creates a Docker image. It creates a container. But at the same time, a request is sent to the render file system that we saw before. The job gets submitted. So the test definitions are pulled from the central database. Okay, now we have the test itself also tells us where to go and get the resources needed for running the test, like the geometry resources, everything that is needed, so the assets. So once it gets here, Deadline receives this package containing the test descriptions, and it says, okay, so for this test, do I have available computers? Yes, okay, so this computer, this worker is going to take this test, or perhaps they're all busy, so let me create another couple of workers and distribute the test there. So this actually is like a harpsichord, like it gets bigger and it shrinks accordingly. So each computer executes a test at a time. What happens after the test is ready, there's another Lambda, which takes the result of the test and creates a reporting for that. So it compares the image to the expected image. It compares the KPIs to the expected KPIs. And through the criteria described in the test, it decides whether the test has failed or not. The report is created anyway, but there is also this blue or red outcome, the test that tells me it has failed or has it worked. So if all the tests are successful, the Lambda itself will unlock the pull request. So that specific criteria will be unlocked. And essentially what we're saying is that from the test point of view, you're good to go. Are there any other criteria? Yes, probably there's a peer review criteria that needs to be satisfied as well. So once that one is satisfied as well, you're good to merge the pull request. Does this guarantee no regressions, no problems? Probably not. But it does mitigate a lot. Because you see the problem here, if this isn't done, the risk is 4 or 5 pull requests are merged into the stable branch. Everything works because they've been tested. The features, everything has been tested, but 2 weeks later, someone tries a feature that is far away in terms of code, far away from what has been worked on, and it has regressed. And everybody says, hey, I haven't touched that in months. And okay, what did we touch in the last weeks? This, and that. Okay, good luck finding the problem. So this actually helps with that a lot. It gets rid of that for sure, 100%. So that is our large-scale automation system. And this is an example of the reporting. So we have visual comparison, we have KPIs. In this case, it's quite a successful reporting. And this is an example of reporting coming right on the telephone of the developer. So it's pretty ubiquitous. Basically, it can be, you can't have your lunch break. You'll be bugged by the system, like this didn't work, go back to work. But yeah, that is actually pretty cool. So in case there is a problem, in case the whole machine didn't succeed, clearly you need to go back and look at your code and see what could possibly have happened and fix it. Otherwise, you won't be able to do the merge. And that concludes my introduction, which was pretty wild because we went from describing chips and how to make them all the way to software of different kinds and how to test them. But and like I said, it's a bit of a cross-section of things we do. So if you have any particular questions about also regarding other areas that we didn't discuss here, you're welcome to try. It's highly interdisciplinary work. I am a software specialist, so be merciful, but we can try to answer your questions.